or in the other meeting that this is an anniversary. It's the 25th STARS talk and the first one in Visio. We've been in Zoom, all the other ones. It's about the width of knowledge within the Alliance. This time we will have a presentation given by our colleague Nicolas Andreff from University Marie et Louis Pasteur in France on how can the robotics industry cope with the planet boundaries. And it's based on a very recent publication at the conference, I believe. So it's from the thematic interest group of sustainable industry that we hold at the STARS EU Alliance. And also to inform you that this will be recorded as part of the how we try to distribute the information so people that are not able to attend could see it afterwards. So I hope that you all are fine with that. Otherwise, that you need to inform because your name could be here, could be seen, and your face could be visible in the recording that we are making for this. But I hope that's fine for you. By this, I will hand the word and the presentation to Nicolas. And after his presentation, there will be a possibility of some questions and answers and some dialogue afterwards as well. So please, Nicolas, the floor is yours.
Okay, thank you, Gunnar. I hope you see all my slides. You all see my slides. Okay, so yeah, this talk is about how can the robotics industry cope with the planet boundaries. It will be a summary of the workshop we held at the European Robotics Forum last March. It was organized by Franziska, Kirstein, Thomas Heidegger, and myself. And you have here the outline, and I will reuse the material that the authors, the speakers at that workshop have provided to me for this talk, plus I will add a little bit of personal thoughts on that. So, as you know, our planet is bounded. It's geometrically bounded because it's a sphere of some 12,000 kilometers of diameter, lost in an infinite emptiness. But it is also bounded from biophysical viewpoints. As you may know, Johan Rockström and others at the Stockholm Resilience Center, they have identified 9 boundaries, biophysical boundaries, that define a safe operating space for humanity, as long as we don't overpass those boundaries. And unfortunately, currently 7 of them have been transgressed with consequences on our habitat. But our planet is bounded, but our society has needs. So Kate Raworth added some boundaries also, but those are social boundaries, 12 social boundaries. And with those lower social boundaries and the 9 upper geophysical boundaries, one can define a donut, which is the safe and just space for humanity, which is the so-called donut economics theory. And of course, you can draw the donut for everything, for the whole planet, for several countries, for even individual institutions. At Lausanne, they have done that. And this donut evolves with time. And as you see on the right-hand side, it doesn't evolve in the correct direction in most of the cases. And those needs, they cost resources and they require technology. So it means that we have to dig materials from Earth. And you see on the left-hand side what is the tension on all the natural elements. If it's red, it means that there are tension on the procurement of those materials. And it is this is a chemist viewpoint. And on the right-hand side, you have the European Union economist viewpoint, where they have tried to identify what are the critical raw materials to which applications and sectors they are needed, and through which technologies they go through. And you see that there are a lot of red in there. And let's zoom a little bit in that picture here to see that there's a very high tension on rare earth elements, which is not surprising because they are the materials that are used to make magnets, and magnets are made for either being in wind turbines to convert mechanical energy into electricity, or in traction motors to transform electricity in mechanical motion. And those apply to the sectors of renewables and e-mobility. And of course, since we have a limit on those rare earth materials, we cannot produce as much energy as we would need to consume for our e-mobility. So there are trade-offs to be found, balance to be found between the use of those materials. For robotics, this picture is really appealing because not only robotics appears in the picture as a consumer of magnets, of course, for the motors, but also because robotics accelerates the production of everything in that picture, because robotics is behind the production of all the technological elements that are in the middle of the picture. You need robots to assemble batteries or fuel cells. You need robots or machine tools to build wind turbines, to assemble traction motors and manufacture them, etc. So robotics is really at the heart of the industry. Since its invention, it has been used to accelerate the production, which has been a positive trend to human progress. But now it is also at the heart of the human degress because it consumes a lot of critical resources on its own, but also for providing the other technologies. And robotics has become very pregnant in our society, and there are some American idiot that believes that we should have one humanoid robot for each human living body. So about 10 billion humanoid robots are its goal. But someone has made an accountant of how much material it will need to build so many robots, so many humanoid robots only. And for instance, they have counted that you need 4 times the annual production of copper to build all those humanoid robots. So it means that if we want to build those 10 billion humanoid robots, we have to live 4 years without copper. That means without building new, say, electric guitars, no more new electric stove, no more new car, new phone, nothing. Okay, but it's even worse if you look at the NdFeB, which is neodymium iron bore, which is the core alloy that is used for magnets. If we were to build 10 billion humanoid robots, we would need 186 years of world material production. So even if we divide this by 1,000, 10 million robots, and imagine you do that each year, it would require 18.6% of the annual world production of magnets. So it means 20% of all that will be taken from all the magnets you need for windmills, for wind turbines, sorry, for cars, for trains, for just repairing your vacuum cleaner, whatever. So it is evident that if you build humanoid robots and robots in general and machines in general, there is a crucial question that has to be asked, which is who will be deprived of what crucial need because of the production of that humanoid robot or that technology. So there is a problem of competition, eviction, and of course we see that by the wars in Ukraine, and which is about rare earth, and in Iran, which is about petrol and energy, that those have consequences. So robotics industry now is also constrained by economic objectives. And well, I'm not a robot, I'm not an economist, but well, I can do a little bit of math. And I read that in the EU, there's an economic motto that there should be an annual growth of 3% per year. But 3% annual growth per year, if you do a bit of math, of gymnasium math, teenage math, you easily show that this becomes an exponential curve, that the production has to grow exponentially, that the resource use will grow exponentially, that the pollution, the wars, etc., will exponentially grow. And the growth here, the exponential growth is cursed, because an exponential growth is unbounded. So it means that it would at some time reach the limit of the resources available on Earth, which is here normalized to 1 Earth. But again, another stupid idiot in the US said, oh, but let's colonize Mars and go for a second planet. At that rate of 3% growth a year, simple math equations show that you have less than 25 years of extra time before you have not only exploited the Earth, but also the planet B. And this is optimistic because it doesn't account for the fact that Mars is smaller than Earth, and then we need resources to go there. So the conclusion of that is that there is no planet B that help us much with our problem here. In fact, degrowth is inevitable. It has been shown since 50 years or so now by the Meadows or Rome report, which was called Limits of Growth. And it shows that as the resources are being taken away from Earth, then they are less and less available. And that has an impact on the industrial production. As you have resources taken, then you increase the production. But at some point of time, this depletion of resources creates a degrowth of the industrial production and for all the rest of indicators also. So economics is constraining robotics industry, but economics is bounded by the planet boundaries, and then the loop is closed. And not only, and so there is no planet B, as we said, but where is that? Yeah, I missed something. Okay, so let's find for B plan. So tentative plan B is not to go for planet B, but for circular economy. So circular economy is an alternative to the current linear economy, which is take, make, use, dispose, which is the pattern of growth, and it's even faster every day because you want this 3% annual growth. And we want to stop that, and this is a European Parliament video that you have here, and go to a circular economy, which would probably manufacture the product and then recycle it and reuse the material for new manufacturing. But the circular economy is a misleading framework, as you can see by those pictures that are quite the same, but that can be found on the internet easily. That let people think that with circular economy, you won't have any waste anymore. But that's not true. That doesn't work like this, because there are no closed loops in engineering. If you have the ideal circle here of circular economy, actually it's not turning around infinitely because you have material and energy loss in this circle here. So if you want to keep this circle going round and around, you need to bring a lot of energy and even more material to that. And actually, that doesn't work like this, because this is how real systems behave. Linear economy goes directly to an end where there is no resource anymore. Okay, so you maximize the financial benefits in an exponential growth, and this is what is known as the fast crash. You will crash rapidly into a world with no resource left. The circular economy means that starting from here, you will come back to the same point after some time, But that has the assumption that there is no physical loss, which cannot be avoided, that you do not extract resources or generate new energy. It means also that you don't have any profit then. And if we have all this, maybe we will go for a prehistoric dash with a circular economy. But in any case, it's not possible because it's impossible to have a system without physical loss. So that turns this circle into a spiral. And this spiral, the rate of convergence of this spiral depends on the losses, but it depends on the consumed resources. As you see here, if you consume as fast as you can in the linear economy, you bring this spiral to one limit, which is the straight line. And if you consume nothing and have no loss, then you bring the spiral to the ideal circle. But it doesn't happen. And this is a problem that we're talking about circular economy because it creates frustration. If you explain people that there will be 100% recycling and zero loss, perfect circularity, then it creates unrealistic technical targets that we cannot meet. And of course, that generates frustration because people will measure the gap between what is promised and the reality. And that is terrible because it will create a loss of credibility about that idea of circularity, and then people will tend to stop making efforts. So the actual plan B is to account for this spiral and not a circle. And the way engineers and roboticists in particular can account for this spiral economy is now to design for evolution, to build for durability, and also to do the design in order that maintenance and upgrade will be facilitated. No one single use product anymore. And we go into a world where maintain, repair, upgrade, reuse are prevalent, and we recycle only what cannot continue evolving. And of course, there are things that cannot be recycled, so that those are lost, those are waste. Why do we stress out that? It's because this circular language is a problem. Sustainability in itself is not the problem. It's not a problem. It's the way we frame it, the way we word that problem of sustainability. And when the language ignores physical limits like circular economy, then models follow. And when models ignore physical limits, then expectation fails. So the conclusion of all that is that sustainable industry must be designed with the same constraints that govern all engineering systems, which I can rephrase as, well, economics can't be separated from physics as it is done still now. And let's come back a bit more to economy, and this is a question of how fast this spiral will converge. And this is a matter of competitiveness, or even a matter for competitiveness. How can we support industrial sustainability? At least how can robotics support this industrial sustainability and not undermine it? Undermining the industrial sustainability will be continuing it, accelerating the production ever and ever, which will go to the crash. But how can we support this industrial sustainability as roboticists? And for that, our colleague Beata Kwiatek told us about the Industrial Accelerator Act, which is a new a recommendation from the EU, and how it could seed sustainable robotic markets. And so why does it matter that we have a new European framework for the industry in that spiral? Because it is based on Europe's strengths. It allows to have some regulation. We can rely on interdisciplinary research, and we can support social and environmental standards. Those are the European society markers. And under those markers, the central question for roboticists are, what kind of robotics future are we building? And as we said, there is a question on how we do that from a technical viewpoint, but how can we leverage that from a policy level. And this Industrial Accelerator Act, which is also known as the Made in Europe Act, which has just come out in the beginning of March, it makes procurement and investment a strategic tool to reward repairable, low carbon, and interoperable robotics. So it creates a framework where virtuous robotics will be rewarded with respect to say vicious robotics. And in this IAA, there are principles and trade-offs that are implemented. And I have underlined here in Beata's presentation things that are very important. Standards. Standards are supported by this act because standard is a way for modularity and reusability and repairability. Also, this is the first time in an industrial act that we see this measure of the impacts of life cycle of the products with standard, again, life cycle assessment and energy per task protocols. But energy per task can be very, very good criterion if you have a very good efficiency, but it usually creates rebounds, known also as the Jevons effects. And in this Industrial Accelerator Act, there's also the accountants for this rebound effect and how to assess it and how to report it so that all the efforts that can be done in life cycle assessments and improvement and optimization will not create even more consumptions. So the conclusion is that Europe's advantage is at deploying the right robots. Those are robots that are durable, repairable, low carbon, and as circular as possible. And it means that competitiveness now is not measured by the scale of the market, but on how it is resilient and sustainable. And information technology should help us go for this resilience and sustainability. The last talk was given by Oussama Khatib, which is a famous roboticist in Stanford. And I want to highlight 2 points he showed us. One is the creation in 2022 of the School of Sustainability at Stanford. And I just picked on their website this citation that the problems are now too complex, that they are putting too fast to make progress in the traditional disciplinary way. And so we have to co-create solutions from the start to address issues in sustainability and climate. So interdisciplinary is a key to our problems. And at the School of Sustainability, as Oussama Khatib told us, they have involved various departments, and all those departments work together. And for instance, Oussama, who was doing a lot of robotics for a long time, he was a pioneer of robotics and industrial robotics, now does Ocean 1K, which is a humanoid robot that is a diving robot. And he has redirected his activity towards something that has some meaning for humanity and not for production. So he's exploring a lot of vessels that have been drowned and that cannot be explored by human divers. So to conclude about that, if I should draw conclusions of all those presentations and a little bit of added thought is to try to find guidelines for sustainable robotics. The first guidelines are not technical and should not be technical. The first one is to think about the balance between the needs and the privation. Usually the needs are coming from the western and northern part of the planet, and the deprivation affects basically the south. And robotics is mainly on the higher part of Maslow's hierarchy of needs, because it's very cool to do robotics. So it's a lot of self-actualization, self-esteem that is involved in robotics and all those new things based on computer science. But actually, what we need is to address the physical needs, to eat, to breathe fresh air, to drink pure water, etc. We need to have some safety in our life. We need to have healthcare, etc. So one way of doing sustainable robotics is to do an ecological redirection. So to use robotics for appropriate needs and functions. Another thing is related to the spiral economy. The speed along which we travel this spiral depends on how fast we're using the resources. And I did a little bit of calculation with my ideal exponential growth, and replacing the growth rate of 3% per year to 2% will give us, well, 49 extra years to live on our planet before we reached its limits. So just slowing a little bit down has more effect than rushing towards a potential Mars. But if you slow down to only 1% growth, then we have an extension of 200 years before we reach the limits. Again, this is a very simplistic model. What we could do is to have a curve with a degrowth, with actual degrowth of economy, but then a degrowth would have a very fast converging exponential decreasing, which is not very acceptable from social matters. But I did just one simple thing. If we start with 3% this year, and then we reduce by 1% next year of this growth. So next year, we require only 2.99. And then the year after, we reduce by this growth by another 1%. So we still have a 2.19, about 8%. Then we reach here an asymptotic convergence to the limit, where at the end we have a 0% growth. But this happened in a time where, well, even our grandchildren will not be there anymore. So maybe we can live with that. So this goes towards a soft landing of the industry, and robotics have a strong role in that also. And the technical part in those guidelines is what is gathers most of the commitment from the robotics community, those who are committed to sustainability, at least, which is a little margin of the community, is to do eco-design, where you try to increase the efficiency of the design, you try to optimize the system you're building. But as this robotics eco label, this new robotics eco label shows it, we should not only assess the quality of our robots on their optimality, but also on how much resources they are using, how much do they allow for repairability, and how can we dismantle them and recycle them and put them into the circle or back into the spiral, and how much of the resource on Earth we can preserve also. And the last slide is about, well, the 9 R's for sustainability. The number of R's depend on the people. I've seen various versions from 4 R's to, well, actually, it's like C++. Each time you talk about a model with 9 R's, then there's probably someone with a 10 R going up somewhere. But those R's for sustainability is a good framework for thinking, because first you have to rethink and rethink the need and to respect the planet, and you can refuse to do things. And once you have accepted to do them, then you should reduce the resources you're using. And then once you have reduced those in the design of your system, you should make this system reusable. And when you don't use it anymore, you could rehome it, to place it, to move it to someone else who would have a use of it. And when nobody can use it anymore because it's broken, you can repair it, or you can even repurpose part of the system to do another system. Another R is not in this chain here, is to restore Earth, to do, for instance, climate robotics, to restore the biodiversity on Earth, and of course recycling and rot. But those are things that are quite easily addressed by roboticists. I'm pretty sure there will be people in the rotting thing that will ask roboticists to do that. For instance, we're burying nuclear waste. It's probably robots that will do that rather than human beings. Recycling is also a very hot topic in robotics now. But it's very important to understand that recycling is just the last thing you have to do. You have to do all the other things first if you want to have the spiral going closer as possible to the circle. And this has consequences both on robotics and economy. For instance, in a rethink respect, you have to do a needs analysis. So this analysis has to be made from an economic viewpoint, also from a robotic viewpoint. And you can refuse to be the robot. My motto is in French, is La robotique, c'est pas automatique. It comes from the fact that antibiotics are not mandatory and robotics is not mandatory either. Sometimes it's useful to have a robot, but it's not necessary at all time. It's not because we have a robot that it is useful. And we can discuss that maybe during the question session. And I stop here because I want you to have time to ask those questions.
Thank you very much, Nicolas, for this interesting presentation. And there's a lot of food for thoughts here that we hopefully could discuss and have some input and dialogue on. So I'll leave the floor open for if there's anybody that wants to start up and have some comment or question to Nicolas at this time. Nobody raising. Yes, Andreas, please go ahead.
Yeah, so my question would be if you already, or if I'm already building a robot that has to compete with other robots in the industry, so and I'm able to use less resources, then I could probably also sell them for cheaper. So there's maybe already some incentive for building robots that use less materials or for recycling robots. Do you know if there's already something in that regard, or is this already looked at?
It has been looked at by Jevon since 1 century ago, but machines for how was that? Steam machines. If you're building a robot that is less greedy in resources, then the risk is that you will have a rebound effect. That instead of selling for less money, you will even sell it for more money because it's better than the other one, and you might. And since it has some green advantage over the competitors, you might even sell it for, or you can either sell it for more money because it's more valuable, or you reduce actually the price, and then more people will buy your system. And in the end, you will have produced more robots than if you had not improved it. So that's why it's important to think interdisciplinary between roboticists and economists to avoid this rebound effect. And I think roboticists can't do much about that. It's about economists to work on that, because they have to understand that a 3% growth, and in robotics it's rather a 10 or 15% growth that is expected. It's not sustainable, and we need to be able to say, okay, we have reached our objective of 2.5% this year. That's it. We don't produce more because it's out of the sustainability boundary. But that's hard to say so.
Yes, thank you very much for this interesting question, Andreas, and your answer, Nicholas. And anybody else that wants to contribute or to have some comment? Yes, Aaron, please.
Hi, do you hear me?
Yes, we hear you.
Excellent. Well, first of all, I'd like to thank Nikolai. It was an awesome presentation, very rich of information and knowledge. And I just have got one question about the environmental impact. Sorry. So, can robotics meaningfully reduce net environmental impact by improving efficiency in other sectors like agriculture, energy, logistics? What would be these conditions to actually, say that this claim is actually true?
Can you put that question again? I'm not sure I understood
Yeah,
correctly.
just for sure. So, talking about environment, can robotics meaningfully reduce net environmental impact by improving efficiency in other sectors, for example?
That's a question. Um, in agriculture, people tend to agree, or roboticists in agriculture tend to agree that using robots can reduce the amount of entrance you will need. You will reduce chemical entrance like fertilizers and pesticides if you have a mechanical action that is done with a robot. So there are people that think about that and say that robotics can have, of course, the robot itself will have an impact, but it will help reducing the impact of agriculture with respect to conventional practices. Now, we have to be clear also, every human activity has an impact, and whatever we do, we are stuck on this spiral, and the spiral is not a circle. So at the end, we will disappear because we won't have any resource left. So the impact is always negative. It cannot be positive. But we can hope that in some cases, robots can help have a less negative impact than without a robot.
Okay, perfect. So that actually makes me think about the space. For example, you mentioned at the beginning about aerospace and defense. So if we talk about aerospace robotics, for example, do you think we should take all these criteria in account as well, or not really?
Yeah, that's also a big question. People want to travel, they want to take planes to go and travel the Earth, because flight was the dream of man. And I think we have achieved it, and now we have to say, okay, we've done that. Maybe we can stop that because it's too costly. But still, having been able to fly planes, to send satellite in space, is probably still worth it because satellites inform us about, for instance, meteorology, which help us to circumvent or prepare us to for instance, events, climatic events like storms or floods. We can prepare that thanks to this observation from space. And also, we cannot completely close the door to living that planet someday towards some other inhabitable planet. But this is not something we can do in our lifetime.
Okay, awesome. Thank you so much, Professor.
Yes, thank you very much. I think time is approaching. There's still a couple of minutes left, though. I think that, if I may, I'll would say that it's a very interesting and important question that you raise about the of course biological. You need to know, you would know that there are resources used in whatever you do. We don't have the perpetuum mobile that doesn't have any friction, any costs at all, regardless if it's energy or materials or whatever. So in the long run, we need to think about what we actually do produce and how we are able to actually recycle and have multiple use of different things and so on. So it's a really, really important issue that you're raising here, depending on that we have one planet, we have an endless amount of commodities and materials and things that we use as humans. So we need to do this very, very shortly and have this thinking into what we actually consume and what we use and how we use it, what's the benefit and what's the use for it. So I would say that this has been an eye opener for me in many things, and that you actually think about this. I'm not in robotics. I'm not into engineering at all, but I'm more into social science and the applied use of IT and such. But of course, it's similar and important how we think about this. So I'm really happy to have listened to this presentation, and thank you very much, Nicholas, for giving it, and was very nice and very, very important and an eye opener for me. So thank you very much. Yes, we have in the chat as well from Andreas. I don't know. Would you like to speak it out as well? We have a minute too, yes.
Yeah, so I have this, we have a fleet of this Turtlebot robots. Maybe you can see it in the camera. And these are already quite older robots. They are now 5 years old, and they came with Raspberry Pi 3. And we just updated them to Raspberry Pi 5, updated a lot of other hardware components. So we can still use this. It's relatively easy to extend because everything is open, so the software is open, the hardware is open. I can just turn out things and put other things in. So that's something that's also very important in robotics. I think that we have this open platform, so people can actually use this stuff for longer times and extend hard and software for new tasks and also change them when they get old.
Yeah, that's an excellent point. Actually, this Turtlebot is designed for modularity because it's aiming at researchers who constantly change the purpose of the hardware they bought. But you would never sell that to a conventional customer because you don't, or the prevalent economic model is that you don't want this customer to modify and be able to repair that robot him or herself. So the one issue in robotics industry is the business model it is built on, and that's why Louise said we should bid for maintainability, repairability, modularity, which is actually what is done with the Turtlebot, with also open software which you can update and upgrade, etc. So this is very important. This approach on open software, open hardware goes in the correct direction. It's just a matter of, again, we're optimizing things, we're increasing the modularity, the reusability, but we have to be careful of the rebound effect.
Yes, and by that, I think you got the final word, Nicholas. Thank you again for giving this interesting talk, and for those that wants to listen to further talks, there will be talks in May and June as well from the STARS talks. They will be advertised through our channels for news and through the website. The next one will be by the thematic interest groups of arts and creative industry, of a new pedagogical approach for teaching arts. So we are having quite a variety of different topics, from robotics to teaching arts in the next presentation. But we have a large variety of knowledge and very knowledgeable and interesting person to give the talk as well. So thank you again, Nicolas, and thank you all for participating today.
Thank you all, and my pleasure.
Thank you. Ciao, ciao.